Yeah, thank you. Thanks very much, and thanks very much to the organizer for the very nice conference and mostly very nice hospitality in this wonderful place. The only problem is that tomorrow we're leaving. So yeah, how to prove finite generation. So let me go straight to the point. So basically, it turns out that it's simple to prove something stronger. So let me fix the setup. Oh, sorry. Since it's here, I should say that it's a joint work with James McKernan. Okay, so the setup here is going to be X is always a projective variety of dimension n, and it's always, we're always working over complex numbers. And then we will have some hypersurfaces, some prime divisors in X, such that if you look at the pair X sum of the SI, this is log smooth, which means that X is smooth, all the SI are smooth, and they are simple normal crossing. Okay, and then again, just so that I don't need to repeat it all the time, A for me will be always an ample Q divisor. So it's a divisor with rational coefficients for which some multiple is going to be ample. So again, we're working on smooth varieties, so I don't need to distinguish divisors from Cartier divisor and so on. Okay, so just now I said we need to prove, we will prove something stronger, be stronger. And this was actually already in the proof of Vladimir Lazic that I mentioned on Friday, I think, on Saturday. So what is something stronger? It's basically what we'll call, maybe I should write it here so that I can keep it. So theorem B. And there is a reason why we call it theorem B. Which says that assume that we have some divisors Bi which are linear combination of the divisor which we fixed there. So the supports of all these divisors are always the sum, the union of all the Sj. Okay, with Bij within 0 and 1 included. Okay, and assume that there exists K for which all this number, all this divisor, so Ka plus Bi are, which actually I should call delta I, but anyway, are integral. So just multiply by for a sufficiently divisible integer. And assume that they are linearly equivalent to some di. Okay, just you could say equal. I'm not assuming that they're effective or anything like that. Just that later on I will choose my own di, so I prefer to use this notation. Okay, then the Cox ring associated to this di, which is the direct sum of all the global section of all the tensor powers of this di, it's finitely generated. So I should say then this is finitely generated. Yeah, exactly. So I should say what? Yeah, exactly. So, okay, thanks. There is not is not, this one is not going to change, so maybe I should say kx plus a plus bi, yes. Thanks. Okay, this guy is finitely generated. So if we only care about one divisor, so only one bi, then this is the classical theorem of finite generation. Okay, so why do we call theorem? Something's missing?
Well, I mean, yeah, the sum of the m.
Oh, sum over the m and sum of so over I. So m can be any integer, positive integer, and I goes from 1 to whatever the bi are.
Is there one thing or several things?
There are several di's.
Right. And
So I goes from 1 to k, say.
The notation m times d means what?
M can be any m times di. So I take any m, which is any positive integer, and any I, which is from 1 to k, and then I take all this possible combination. Yeah, actually I shouldn't have written here, but anyway. Okay. So, okay. So there is one reason why we call it theorem BA. So because it's related, strictly related. And this was also in BCHM with another theorem, which is called effective non-vanishing. Which says that if we take this object, which is the set of all the B1 pair, vectors B1, BK, BQ, sorry, inner Q, action 0, 1, Q, such that if you look at Kx plus A, which is my fixed ample Q divisor, plus the sum of BI SI. This is linearly equivalent, Q linearly equivalent, or R linear equivalent, which means that the difference is some linear combination of principal divisor to some divisor D for some D effective. Okay, I will comment on this very soon, but basically let me tell you the theorem. The theorem says that if this is Q, then Q is a rational polytope. Okay, so let me remind you what is a rational polytope, first of all. A rational polytope is just a subset of Rn, which is convex. It's called the rational polytope. If, first of all, it's compact, and then it's defined by a finite number of hyperplanes. So it's, and C is the intersection of rational hyperplane, yes, that's it. Of rational half spaces. Okay, so just think of something like this. Okay, so the word compact plays an important role here because it means that. Okay, James. I'm going to have exactly the same problem with James, but let's stay here. Okay, why the word compact plays an important role? Because it means that it's closed. So Q is closed. What does it mean? It means that if an object of this form here is Z-effective, meaning that it's the limit of some big divisor, then it's also going to be effective. So the fact that this is closed, it's already a very important statement inside theorem A. The other thing that plays a very important role is that it's defined by a finite number of vertices, or extreme points. So, let me fix this first. Okay, sorry. So basically, that's the reason why it's called effective non-vanishing. Because every divisor here if you take any delta inside here, basically you can find a divisor which is linearly equivalent to kx plus delta just by looking at the vertices, okay, because the vertices span everything here. Okay, so that's somehow, it's clear somehow these two theorems are related within each other. So the purpose of this talk is to see exactly how they're related. Okay, so first of all, let me say some applications of these two theorems.
So I'm sorry, can we go back? I mean,
Sure.
we're talking about adjoint divisors, so there's always kx plus something.
That's right.
And so this Q is, should we think of it as centered at the point K?
So
this is not linear.
Yeah, so-
we're doing linear algebra, we're doing affine algebra.
that's right. So this one does not correspond to some delta. It's a one-to-one corresponding to some delta. Yes, that's right. That's right. There is a one-to-one and some more.
Where's the kx there? Is the kx an internal point of that?
No, this is just a, if you want, this is just a vector b1 bk.
Yes.
So, but there is also, if you look at some vectors.
Is in that plane?
No, this one it's rk, so we don't even care about kx. There is no kx here. This is just some
That's just a definition. But in the theorem?
kx. It's always the same. So yeah, it's some kind of, it leaves, I mean, usually the way we denote it is to work on vector space of divisors. We only care about this, and kx is fixed. So it does not play any role, kx. So you have a subset.
If you get to add two of those things together, then you're adding something with kx plus something with kx. So you
That's
get
right.
2kx.
That's right. So it doesn't mean that it must contain the origin, but it doesn't matter.
Right, it's an it's an affine convex polytope.
Yeah, but what is?
Okay,
Yeah. So the origin could be somewhere here. I mean,
Yeah.
I mean, in this picture it's always inside, but no, actually it's not even inside. Yeah, the origin could be somewhere here. Doesn't matter.
Yeah.
Okay, so yeah, the important thing basically is that there are a finite number of delta I for which, if you look at the corresponding D, this D generates all the others basically. So the application is of these two statements is that, first of all, this was mentioned already, I think on Sunday, that any finite variety is a monodream space. So very briefly, what it means is that any finite variety can be embedded in a toric variety, which from a Mori point of view, from Mori program point of view, it contains pretty much all the information. So it's a very nice way to study finite varieties. The second property is that, and this was mentioned in James' talk at the AMS, the minimum of the program can be shown that from these two theorems, the minimum of the program with scaling always terminate. And it's also related to point 1. So what I'm trying to say here, I'm not going to talk about minimum of the program with scaling, but what I'm trying to say is that from these two theorems, it's pretty much, it's almost elementary to get all the theorems in my previous paper with Birka, Ecker, and McKenna. Okay, so now the question is how to prove it. And on Saturday I talked about the lifting theorem. The lifting theorem is going to be the one of the main tools here. So let me just remind you what the lifting theorem says. Okay, so we have this setting here still. Okay, let's suppose that delta is of the so I will often choose S to be equal to S1, just to make my notation simpler. Okay, let's assume that delta is of the form S plus A plus B, where B is of the form Bij Sj from 2 to Q, since we already used 1. And Bij are within 1 and 0 and 1. We exclude 1 so that it's PLT. Okay, so it's a Q divisor. So assume that there exists K positive numbers such that k delta is integral. Okay, so and we define A prime exactly like last time to be A divided by K. Okay, and then, okay, this is the real assumption. Assume that there exists a Q divisor D which is effective and such that D is Q linearly equivalent to Kx plus delta plus A prime. So I'm going to comment on this again, and I'm going to remind you what is the role of A prime here. So it's going to be fundamental on proving theorem A. So, but let me say first that ND does not contain any strata of the union of SI. So what this means, this is simple on crossing, so it's very easy to see what the strata are. Just all the possible intersection of all possible subset of these divisors. Then, under this assumption, there is a surjective morphism, which is given by restriction. So this morphism is surjective where theta is defined by adjunction. Okay, so there is another way, equivalent way to see this theorem. Given all this assumption, another equivalent, actually I could delete this. Way to see it is that sure. Okay, so where exactly?
Kx plus
Delta subject to his restriction.
Ks.
K times Ks plus theta, where theta is just defined by adjunction.
Why do you put the double indices on the V?
Oh, this one doesn't have, yes, that's right. Thanks. This one has, so yeah, that's why I got confused. You're right, thanks. Okay, so another way to say it is to lose, you can see this from a linear system point of view instead of, because we're going to use it later. So I'm going to write it. Another way to say it is that the linear system of Kx plus delta restricted to S is the same as the linear system of Ks plus theta. Okay, so this is the equivalent way to say this from a divisor point of view. Okay, so from this, of course, so how to use, sorry, I should have said, I'm going to go back to this, but basically the role that A prime plays here, it's always in our favor. Because again, we're not even assuming that Kx plus delta is set effective. But if you shift it a bit, it becomes somehow, much weaker than assuming something on Kx plus delta itself. I would say why this plays a very important role when we try to prove theorem A in few minutes. But let me continue with the lifting theorem. In general, we don't have this assumption, of course. There is no way that someone can guarantee the existence of this D. But if you assume that things are nice enough, so in general, if we just assume that S is not contained in the stable base locus of Kx plus delta, then from the lifting theorem we can prove something weaker, but it still follows immediately. So in other words, there exists always an omega. I'm not going to say too much about this omega, which is less or equal than theta, and such that where theta is still equal to delta minus S is given by injunction. such that something weaker than this is true. And what is the weaker thing? Well, we need to remove something. We need to remove the piece which gives us something for which this is not true. So in other words, if I look at the right-hand side with omega instead of theta, and then I remember to add it later, this is contained inside the restriction of kx plus delta on S. So in other words, if you take any divisor which satisfies this property, delta, which satisfies this property here, it doesn't matter if this is true or not. If you remove those components for which somehow you get some, of the stable base locus of kx plus delta in an appropriate way, then you can, again, sorry, this is minus, of course, then you can get a lifting of this guy here. Okay, but since we want to work with this guy here, what we do is that we take the whole linear system of kx plus omega multiplied by k, and we add a piece of whatever is missing here, and we had the lifting theorem. Okay, so this says that all the divisors which are linearly equivalent to this, plus this fixed component, it's something can be lifted to kx plus delta. Okay, this is called, we're going to call this property star. Okay, because we'll see in 1 minute that it will be the main ingredient to prove this theorem. Okay, so before I go to theorem A,
quite important that the units make the normal crossing, right?
everything is a normal crossing. I mean, you know what is omega, right? But I only care about one. Okay, so any question? Okay, so how do we continue from here? Again, I'm interested to prove theorem A, so we'll let to understand rational polytope vectors. And one thing we found out is the characterization of rational polytope. So this is really Euclidean geometry property. So suppose this Q is a subset over N, and it's a convex bounded set. Okay, and let's assume that, the statement is that Q is a rational polytope if and only if the following holds. So I don't want to forget anything. For any V inner n, and for any k positive integer, and for any W and Q, such that the following two properties hold. So first of all, kv it's an integer. It's an integral, sorry. It's an integral vector. And the second property is that the difference between v and w in norm is less or equal, whatever the norm is less or equal than epsilon divided by k, sorry. Is less than epsilon divided by k. Okay, so if we have this property for any v, k, and w, then w must be in Q. Okay, so in other words, if you want to check if a convex subset, which is bounded, it's also a rational polytope, and of course this is going to be bounded from the very beginning, Then you just need to check that this property holds. Namely, for any v, k, and w, these two holds. Sorry, and these two holds, this is true. Sorry. Okay, so there is nothing much in this statement. It's just an element. Probably it's already been known for ages.
I'm sorry, at the beginning you've got W in Q, and at the end you've got W in Q.
W in, you're right, sorry, V in Q. That's right, thanks.
Well, it's a true statement.
Yeah, that was, well, it's not a true statement if you put if and if here. Thanks. So yeah, it means that if you can approximate any point inside Q by something which satisfies this property, then also the point itself must be in Q. The other point itself must be in
So
Q.
this is Diophantine approximation.
That's right. This is just Diophantine approximation. It's the only key point of the proof of this lemma. Everything else, it's pretty much obvious. What follows from this lemma is that Q is also compact. We're not assuming a priori that Q is compact, but you can prove that given this property, Q will be compact. And again, it's a, yes, as you said, it's a direct application of the Diophantine approximation. Okay, so why is this very similar to what we need? So we have the lifting theorem here, where we have that something is integral. K delta is integral, and also here something is integral. And also the difference of something, so here there is A prime, which gives us a bit more to go inside the pseudo-phatic cone and to have a nice property. Okay, and this is exactly what we have. If we add a bit more, which is exactly the same order, A prime is of the form A divided by K, and here it's epsilon divided by K, where epsilon is going to be very much related with A, then you see that there is nice property about Kx plus delta. Namely, this is true for Kx plus delta. Okay, so in other words, if you're in neighborhood of this guy here, this convex subset here, since you have that, you can even go a bit outside, but if this property is satisfied, then it means that this also satisfied. And that means that you're not really outside, you're inside, because in particular this means that this is not empty. Okay, so it's basically it's an easy property. It's quite easy to check up that this plus this implies almost what we want. I'm going to say what we want now. So this is going to be the main lemma. And from which everything follows. So bear with me with the definition of Q. It's going to be quite ugly, but it's useful for both lemma Y, theorem A and theorem B. Okay, so I'm going to define Q in quite a nasty way, but it's later on it will probably be a bit more clear why it's useful. Instead of considering only one divisor delta, I'm considering pairs of divisors, delta omega. Well, what is delta? What is omega? Delta is something that of the form something like this. More exactly, it's of the form, since we want to lift section, it's going to be of the form S plus A plus sum from 2 to Q of some bi Si. Okay, omega is something which is within 0 and the usual theta, which is delta minus S reduced to S. Okay, but of course we want a bit more. We want this property to be true. S is not contained in the stable base locus of Kx plus delta. There is no way that we can lift anything if this does not apply. We want to apply lifting, and if S is contained in Kx plus delta, it's easy to check, and nothing works. It's not, thanks, of course. And then the final property is that omega delta satisfies star. Sorry, delta omega satisfies star. That's the crucial point. You want to make sure that this set, which could be a priori very, very ugly, satisfy a lifting theorem. Okay? Then this guy here is a rational polytope. I forgot to say something else. Sorry. The main assumption here is that, okay, it's we proved this by induction. So I'm assuming that theorem B is true in dimension n-1. Which is not too much of a cheating, but we need to do that. And the reason why we need to do that is because we need to be sure that the base locus of kx plus omega is not behaving badly. Okay, so since again I'm proving everything dimension n, it's not too bad to assuming this. Okay, everything is known for curves, so it's okay. Okay, so why does this help? Now let's try to prove theorem A. Oh, let me get rid of this. And let me continue here. Okay, so we want to prove the fact that theorem B in dimension n-1 implies theorem A in dimension n. Okay, so this one here, finite generation of the Cox ring in dimension -1 imply non-vanishing, affecting non-vanishing dimension A. It's almost what we have, what we already have. What is the difference with what is written here and what is written here? Well, first of all, this one works for pairs, but it's okay. We can project to the first factors. It's the whole point about this discussion is that this is it looks somehow much stronger than this. Because if a product is a rational polytope, of course, also the two factors must be a rational polytope. But there is something missing here. It's the assumption that one of the coefficients must be equal to 1. Here, there is no such assumption. Here, any coefficient can be within 0 and 1. So how we go from here to here? Well, and this is pretty classical. It's basically Shokurov idea, and it's also contained in BCHM, and it's very similar to what James was talking about before. So it's also been used by ACU. So we want to prove that we can always reduce to the case that one of the coefficients is equal to 1. So how do we do that? So the idea comes from Nakayama. Which says that if we take any delta, I didn't realize that I denote Q and these two Q are different, so let me call this Q prime. If we take any delta which is somehow corresponding to a point here, unless we are very unlucky to take one which numerical dimension 0, then it means that we can create a low canonical center. So what does this mean? So let me take one divisor delta which is corresponding to something there. Okay, let's assume that it's such that it's set of this such that kx plus delta is set effective. In other words, we are in the boundary of Q. So it's a limit of big divisor. So the idea is that we don't know if the kx plus delta has section, but if we interpret that bit, Nakayama tells us that there are a lot of sections, unless the numerical dimension is equal to 0. So let's assume also that the numerical dimension, whatever it is not 0. So what it means is that it's not numerically equivalent to something which is trivial, I mean numerically, not numerically equivalent to 0, but something which is the stable base locus, augmented stable base locus. Okay, so if you've never seen this before,
You mean strictly greater than 0?
Strictly greater than 0, yes. Equal to 0, I mean, it's going to be greater or equal than 0 because it's set effective. But we are getting greater than 0. What it means is that, in other words, another way to say that is that Okay, so maybe the definition could be just that H0 of mkx plus delta plus ka, where k is a constant for which ka is sample, goes to infinity. Sm goes to infinity. So the whole point here is that most of the divisors delta will satisfy this property. And actually that's all we care about. Okay? Then we can create a low canonical threshold. What does it mean? It means that, again, this is by Nakayama, there exists d greater or equal than 0. Actually, assuming this is the standard argument, such that, first of all, we have that kx plus delta plus 1 over ma, it's q linear equivalent or r linear equivalent to d. So again, we don't know if kx plus delta has any effective divisor corresponding to it, but if we add an ample, for sure we know that. And the multiplicity as any generic point of d is greater or equal than n times m, n divided by m, for some x generic. Okay, so why do we care about this? Well, the reason is because this number is going to be a very important number. Why? Because it means that at least one of the if we are in the, let's cheat a bit, let's suppose that it's also log smooth, which we can always do by taking log resolution. So it means that one of the coefficient of d, it's at least 1 over m, because there cannot be more than n accumulating at one point. Okay, so what does it mean? Let's see what happens for 1 plus, so let's take any t greater than 0. What happened to 1 plus t kx plus delta? This is, again, R linear equivalent to kx plus delta plus t kx plus delta. But t kx plus delta, it's almost the same as d if I subtract 1 over ma. So it's easy to check that what we have here is kx plus m minus ta divided by m, which is the thing that I subtract when I take care of this guy here, plus b, plus td. Okay, this is our obvious calculation. T kx plus delta, it's almost equal to td. Whatever is missing, I'm taking it from here. Okay, and so we call this kx plus delta t. And again, assuming that everything is simple normal crossing, we will reach a point for which one of the coefficients of this guy here is going to be 1, exactly like what we have here. So lambda will be the sup for which this guy here is log canonical. So log canonical just means that one of the coefficients of b plus td is going to be 1. Okay, all the others will be less than 1 or less or equal than 1. Okay, so we arrive to the point for which one of the coefficients exactly like here is going to be 1.
So you're still on x?
I'm still on x. Maybe I should blow up a bit, yeah.
You start on the n-fold x, you blow it up lots and lots of times, you
Not so
mess around
many.
like this, you increase the coefficient t until you hit a threshold.
That's right.
Right, and then you've got, and from that moment onwards we're going to do an induction on the dimension.
No. Oh, yeah, I mean, for this point of view.
Right.
Yes, that's right, that's right, that's right, that's right, yes.
So then you're going to restrict to that one.
No, not anymore, because I already have this theorem. I'm not going to restrict anymore, because I already proved this. Let's suppose that we already proved this theorem. So I'm not going to restrict anymore.
But you have to go back down dimension.
It's already contained here. This is rational polytope. So if you project this q prime into the set of deltas, so into the set of divisors of x, this is already a rational polytope, assuming that one of the coefficients is equal to 1. So I don't need to restrict anymore. The only difference between this and this is that one coefficient is equal to 1. At least one coefficient is equal to 1. So I already restricted before, but I'm not going to restrict anymore.
Yeah, that's the way the restrictions happen.
Exactly. That's exactly where the restriction happens.
In any case, the main point is that you have to change the model X. You have to do all that blowing up.
Yeah, but only once.
And you do it once.
Yes, only once until this looks smooth. That's it. Then I don't do it anymore. Yes, that's right. Exactly. Okay, so exactly what you're saying is correct. So how do we do that exactly? So basically we look at the map. Sorry, we can do this in a neighborhood of delta. What does it mean? Remember, we still have an Apple divisor to play with. So I don't want to write all the details, but basically playing with the ample divisor, I can do this process in a nice way around any delta with the same D here. Because I have a lot of freedom here, basically. This one gives me a lot of freedom because A, it's ample. So basically I can perturb a bit delta, whatever I wrote here is still true. Okay, so what does it mean? It means that I get a linear map which given delta gives me delta lambda. Okay, where delta lambda is exactly like this delta t with t equal to lambda. What is the advantage of doing that? The linear map brings me this rational polytope to something which is simpler than this rational polytope. Sorry, this polytope, or this object, which we don't know what it is, to something which is easier than this rational polytope. So, of course, there are some details to check, but basically this says that this guy here, it's a polytope around delta. And then rationality follows easily. Also the case for which this is not true also follows easily. So I'm going to skip that part. So Q in theorem A, it's polytope around delta. And then it's easy to conclude. So more precisely, it's a polytope around this coefficient here. Okay. Then the fact that it's bounded gives us everything else. So this is pretty much all it's involved to prove theorem A. Okay. Now, how about theorem B? How much time do I have? 15 minutes. Okay, good. How do we want to prove theorem B? So now that we have theorem A, I think at this point I can erase this. Now that we have theorem B, theorem A, it's enough to prove that theorem AN, so theorem A in dimension n implies theorem B in dimension n. Okay, and then the induction goes through. So how do we do that? Well, there are a few steps. So first of all, let me tell you what is step one. So we have some divisor, delta 1, let's say 3, for instance, just to make a simple example. Delta 2 and delta 3, for which we know nothing. We don't know anything about these divisors. We want to show that the Cox ring generated by these three guys, it's finitely generated. So let's take the rational polytope which joins these 3 points, for instance. It could be more than 3, but it doesn't matter. And then remember, Q, it's we know that Q, the one before, was also a rational polytope. So we have a picture like this for Q. Well, remember, Q is the set of all deltas, more or less, for which kx plus delta is effective. So, and of course, when delta is not, kx plus delta is not effective, meaning if we take a point here, it's not going to play any role in the Cox ring. There are no sections here. So we can completely forget about this. So the moral of the story is that we can completely forget about what is outside the blue set and look at the intersections. So I can add a bit more divisors. So let's say this is delta prime 1, delta prime 2, delta prime 3, and so on. delta prime 5 and delta prime 6. And I can say, okay, instead of working with delta 1, delta 2, delta 3, let's work with the delta primes. We didn't lose any information because here there are no sections whatsoever because it's not even effective. So the first step, say, we can assume that those di that we had at the beginning, which were linearly equivalent to kx plus delta I, are effective. Okay, so this is, in this point here is the only time where we use theorem A. So from here on, you can forget about theorem A.
So I can't read what it's written.
So we can assume
di twiddles.
k times kx plus delta I. So at the beginning, we had this. The di was linearly equivalent to kx plus delta I. And then now we can assume that these di are effective because I just do this game.
And this is linear equivalence, isn't it?
This is linear because I took k sufficiently large. Yes, this is linear equivalence. Okay, so this is step 1. And again, we can forget about theorem A at this point. So what is step 2? Step 2 will be similar to what we did with the Nakayama just now. Mainly, we want to go to some canonical threshold. But the way we do it is slightly different. So we define W to be the set, the vector space spanned by the component of the di. So this is step 2, sorry. Okay, and then what do we do? Basically, we want to go to some kind of canonical threshold. So we define spanned by the components, sorry. I forgot one word.
I mean, you mean a subvector space of a given vector space?
Yeah, the vector space of divisors on X.
Inside the vector.
So let's say, since there is no difference between the device, let's make the notation simpler. So the R divisor of X. So the components, sorry, I forgot to say that. Okay, and then we consider a new polytope, which is automatically a rational polytope. So I'm going to call it R, which is the set of all the delta plus G, such that delta is a linear combination of the delta I, where Ri, the sum of Ri is equal to 1, and Ri are positive. So I'm going to draw a picture in 1 minute so that this one will be clear. But anyway, G will be inside W, and will be effective. Okay, so what is going on? Let's assume that there are 2 deltas now to make my picture a bit easier. Let's suppose that we only have delta 1 and delta 2. Let's suppose that, so they span something like a line or something like that. So I'm going to work on a bigger vector space, and in which I consider also the components of d1 and dk. So since I consider them with positive coefficient, I'm only going either to the right or above. Okay, I forgot to say something, which is such that delta plus G is log canonical, of course. So no coefficient is bigger than 1, of course, otherwise we cannot do minimal model program. Okay, so we stop when we reach 1. So this is R somehow. Okay, so what is this picture? Basically, we add an extra component, an extra direction to the vector space, which is defined by delta. So all these are basically the delta. And then we go somehow increasing G in this direction. Okay, so why do we care about this? Well, the reason why we care about this is because this side here has at least one component, also this one here. At least one component of delta plus G has coefficient 1. And why do we care? Because again, remember, we like to apply adjunction. So we like to have one component with coefficient equal to 1. Okay, so this is step 2. The step 3, so this is also a rational polytope, sorry, I should have said. And it follows immediately from the definition. And so we can replace delta 1, delta 2 by all the vertices of this rational polytope. So I just increase, I call this delta 3, this delta 4, and this delta 5. Okay, so we're almost done. What is step 3? So one thing that appears clearly from this definition is that if you take gamma, which is an element inside R, then there exists D greater or equal than 0 with D in W, such that Kx plus gamma is R linearly equivalent to D. Okay, because it was true for delta. So if I add something which is still in W, surely this is going to be true. Okay, so what do we do now? We do exactly the same as we did before. We go to the low canonical threshold. So how do we do that? We consider gamma t to be just equal to gamma plus tg. I'm cheating also a bit. I should have said that we can assume that d1, dk are simple normal crossing, but I should have done this from the very beginning so that I don't need to worry about it. TD, thanks. Okay, so what is the picture? The picture is very easy. The picture is that we take any point inside here. This is delta. And then we start to sum, sorry, this is gamma. And then we start to look at gamma t. And we do that until we reach this guy here. And why do we care about that? Well, the reason is because it follows immediately that Kx plus gamma is something which we know very well. So more exactly, how is it? Kx plus gamma t, it's the R linear equivalent to Kx plus gamma plus Td. D, yes. Which is equal to, sorry, which is also a linear equivalent to 1 plus t Kx plus gamma. Okay, so I'm moving in a very special direction for which the section do not change, because this is just gamma t is just a multiple Kx plus gamma t is just a multiple Kx plus gamma. So the section of this guy here are exactly the same section as this. So the section of this one here, which is the only one we worry about, it's exactly the section of this guy here. Okay, so what do we get about this? The point is that we can completely forget about what happens here. The only two pieces that we care about are the components with at least one the pieces for which at least one component is coefficient 1. By doing this game, the only two things that we care, if this is the picture, is this guy here and this guy here. Okay, so we only need to prove finite generation. Finite generation of the Cox ring assuming that on each delta I is equal to S plus A plus something else for any delta I. Okay, again, the reason is because we just think that this is completely useless because it doesn't contain any new section. All the sections are contained here and here. Okay, so the last step is that we need to use main lemma again. So by the main lemma, so if you remember, the main lemma says that something which is contained in a product, it's a rational polytope. So now we don't care anymore about the first factor, we care about the second factor. Okay, so, and everything lifts. In the big Q that I defined before in the main lemma, all the section lift by definition of Q itself. Okay, so by the main lemma, we can assume that this is happening on S. That all the sections come from some ks plus omega, where omega lives in a rational Poitov. Inside the set of divisors of S. Okay, why? The most important thing about this statement here is rational Poitov. Lifting theorem we already knew, but since we knew from the main lemma that we had a product, which is, something looks locally like a product, for which the big thing is a rational Poitov, then also the projection S on this guy here will be a rational Poitov. So we don't care, it's not going to be a very ugly object, it's going to be a rational Poitov, the one for which we lift section from. All the omegas which appear here are coming from a rational Poitov. So we just need to use induction. So by induction, we are done. It's okay. Okay, and I'm going to stop here. Thank you.
So you did say the name, but I think it would be fair to write Vlad Lazic on the blackboard.
Yeah, I say, well, yeah, you were not here on Saturday. Yeah.
You're laundering his proof.
Yeah, that's right, yes. We are laundering the proof, yeah.